Hi, I'm Mr. V. Today we're talking illustrative mathematics, Unit 5, which is about solid geometry, and this is lesson number 5, scaling and unscaling. And the objective is by the end of the lesson you should be able to say, I can use square root graphs and do calculations to interpret the relationship between scale factors and areas. And so we start off with this question, which is from Mid-America. I'll move this down a little bit. The image shows the Transamerica building in San Francisco. Notice it's got these wings on the side, but the top floor is right here. It's about a third of the way down from the very top. So the base of this has approximately 53 meters by 44 meters, and the scale factor is 32. And if we ignore the wing sides, what is the area of the top floor? Show and explain your reasoning. And I have two examples here from student work. So the first one, this student wrote the formula. Notice if we have the area that we're going to, it's proportional to the scale factor squared. Why? Because there's a length component and a width component. This times the area 1. So she did this directly and came up with this answer. This other student said, what is the scale factor times 53 is going to be this, times 32 is this much. The scale factor of this times 0.32 is this much, and then multiply those two together to get this. So both of these methods work, both of these ways work, and I'd like to just point out to you in a simple drawing here how this might increase your understanding if you're struggling with this. If you're struggling with it, we're going to be on it for a while, so it's okay. So if I have, I'm just going to draw a figure here like this, and let's just say I have a triangular pyramid, and I'll draw it like this. If I were to have a scale factor of 1, that would be the original object. If I were to have a scale factor of 0, that would be the point of dilation. That's where I'm not going to go through. If I wanted to scale factor this by 1.5, I'm going to go this far and 1.5 times more down to here. This far and 1.5 times more, and this far and 1.5 times more. So I'd end up with something like this. This would be a scale factor larger than 1. So my K factor here is going to be greater than 1. And if I did somewhere in between here, let's just use a different color, like right here. This would be somewhere between 0 and 1. So it's larger than the point of dilation, but it's smaller than the original. So this is going to show you how this works. And if I were taking a length of the side, so each one of these has a length. This is my starting length. And let's just say we're going to some other length down here. I would take my ending length is going to be my scale factor, which is greater than 1, times the length. Well, it's also got a width. And this whole thing has an area too, and this has an area. So since it's got a length and a width, I could write it like this. The area of 1 is going to be the length of 1 times the width of 1. My length 2 is like this. I could also say my width 2 is equal to the scale factor times the width 1. So I could say my area 2 is length 2 times width 2. Notice this is k times length 1 times k times width 1, because I'm just substituting these values for length and width. This is k squared times length 1 times width 1. Oh, that's just my area 2, and this is where we come in with the big formula. Area 2 is equal to k squared times area 1. This is the big idea. So the lengths are proportional to the scale factor. The areas are proportional to the square of the scale factor. And later, we're going to discover that the volume, if we did a volume, it's going to be proportional to the scale factor cubed of the original volume. Okay? That's the big idea between what's going on here. Now, let's see, where are we? Two viewpoints. A triangle is an area of 100 square inches. It's dilated by a scale factor of 0.25. Maya says it's dilated, its triangles are 25 square inches. Lynn says, wait a minute, it's 6.25. With whom do you agree and why? Some student responses. One student said, well, wait, not this one. Sorry. I have this from somewhere else. Sorry. Not mean to do that. Go back to this question here. So, my is incorrect. She multiplied 100 times 0.25. She needs to multiply 100 times 0.25 times 0.25. Let's see if I have any student working here. So because you do 0.25 squared, which is 0.0625, when you multiply it by 100, you get 6.25. So that's how they got this. And I didn't have any students agree with mine on this particular class. Now, here we have this next question. You had to explain to the person why they were wrong. And let's see what the students said. They just took 25 times 100 instead of finding the area correctly. Well, you needed to do it squared. That's what we needed to do. So in this next activity on 5.2, it was calculate the area if the original triangle with an area of 100 square inches is dilated by these scale factors. By 9, well, that's 9 times 9, k squared, times 100, or 8100. For 3/4, it's going to be a little bit different. Here's some student responses. Let's see if I can anonymize these students for some reason. Notice they all get, it's 56.25, 56.25. Did any of them explain why they did that? And it's going to be inches squared or units squared, whatever it is. And why is it 65.25, not 56.25, excuse me. Well, when you multiply 0.75 times 0.75, and you could either do that when you're k squared, and k is k squared, and if k is equal to 0.75, you could write this as 0.75 times 0.75. You could write it as 3/4 squared. You could write it as 3 times 3/4 times 4, which is 9/16. So there's a lot of different ways of getting to the same idea. And that's the k squared. To get to our second area, we have to do the k squared times the area 1. Our area 1 was 100. So when we multiply that times 56.25, which is what this is. I'm sorry, 0.5625. Then we get 56.25. Okay. Questions or discussion? Here we go. An artist painted a 1 square foot painting. Now she wants to create more paintings with different sizes that are all scaled copies of the original. Paint she uses is real expensive, so she wants to know the size that she can create using different amounts of paint. Suppose she has enough to cover 9 square feet. Well, 9 square feet, if I take my original of 1 and my k squared is 9, she can use a scale factor of 3 to do this. How did I get that? I went my area 2 is equal to my scale factor squared times the area 1. Area 1 was 1, area 2 was 9, so k squared is equal to 9. When you take the square root of both sides, we actually get a plus or minus value, but we're going to ignore the negative root because we're dealing with a number of paints or number of scale factor for the paints. So I get k is equal to 3. That's what I'm looking for. And we can do this several times with this value. So we put 0 would give me a 0 factor. 1 would give me 1, 2, 3, 4. Oh, there we go. And when I graph these, it looks like this. So the question is, if you use the graph to estimate the scale factor, she could use to cover 12 square feet. So here's 12 square feet. And we go up, and it looks like it's going to be 3.5, maybe 3.75, somewhere in there if I make a curve out of this. This curve is the square root curve. You'll notice if I have the square root of 4 is 2, the square root of 9 is 3, the square root of 16 is 4. So suppose one has enough to cover 1 square foot, and she buys enough to cover 2 square more. So this would be square root of 3. Square root of 3 is about 1.5. Is that right? 1.7. I'm sorry, 1.7. So it's somewhere in here. And what about if we had 14 and did it 2 extra more? So if we had 14 and did 2 extra more, so we're going from here to here. And notice, even though I'm going up by 2 gallons, the amount of square footage that I'm going up from is very, very small. It's not like going up 2 gallons down here. It's not the same. So on this drawing, if you scale this up by 2, I'm going to go from A, I'm going to go this far, and then I'll go that far again. I'll go this far, and I'll go this far again. So I get to B prime and C prime. I'll go like this, scaled up by 2. Then it says to scale it by -2. I'll do this in a different color. So if you scale this by -2, if this is a scale of 1, -2 is go -1, -2. This would be B double prime. Here, this is 1. I'm going to go 1, 2, way over there somewhere. This would be C double prime. And what transformation is it that moves me from this to this? It looks like it's going to be a rotation. And a rotation, because if I rotate 180 degrees, it will take B to B prime. That is 180 degrees around point A. If I rotate this 180 degrees around point A, I get to C prime. C prime to C double prime, or C double prime to C prime. So it's going to be a 180 degree rotation that would move this figure onto this one. And that was the question for this particular slide. Were these rates the same? Here's some student answers. Oh, by the way, on this slide, I think I give you the answers. Yeah, check your answers. I give you the answers here so you can check your answers. No, they're not the same. And you can check your answers. For the cool down, we have a toy train set. And at the front of the set is a building. And the building on the toy is 1 square foot like this. And on the real building, it's 400 square feet. So my area 2 is equal to 400. My area 1 is equal to 1. And the question is, what is the scale factor? So if you go area 2 is equal to the K squared times the area 1. So we have 400 is equal to K squared. So K is equal to 20. And there's a lesson summary here posted. Notice this is the square root curve. You might be used to the square curve. X squared is a parabola. This is y is equal to x, is the square root of x. So the square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4, and so forth. This is what the square root curve looks like. And that's all I got for today. Good luck and success.